In this section, we are going to consider the boundary value problems. We start consider the very simple differential equations. Second derivative of y with respect to x plus lambda y equals 0. And as a boundary conditions, the value of y becomes 0 at the x equals 0 and x equals a. General solutions. The first case is lambda equals 0. Second derivative of y with respect to x equals 0. So if you integrate one times, this is dy dx is a constant value of the c sub 2. If you integrate one more times, y is given by c sub 1 plus c sub 2x. So this is the general solution when the lambda equals 0. Second case is a lambda equal minus alpha squares. Differential equations. Second derivative of y with respect to x minus alpha square y equals 0. As usual, you can substitute y equal exponential mx. Then m is equal to the plus minus alpha. General solution is expressed c sub 1 exponential alpha x plus c sub 2 exponential minus alpha x. So we could express the general solutions using the exponential functions. But if the regions we consider is finite areas, we have another way to express these solutions is c sub 1 hyperbolic sine alpha x plus c sub 2 hyperbolic cosine alpha x. So you can choose either ones as a general solutions when the lambda equal minus alpha squares. Last case is a lambda equal alpha squares. Then differential equation becomes a second derivative with respect to x plus alpha square y equals 0. Then general solutions. Y is expressed c sub 1 sine alpha x plus c sub 2 cosine alpha x. So this is the general solutions. Then we apply the boundary conditions. The boundary condition is given the value of y equals 0 at the x equals 0 and x equals L. For the first case, you can consider the general solutions is y equals c sub 1 plus c sub 2x. Then at the x equals 0, y 0 equals c sub 1 equals 0. So we could find the c sub 1 equals 0. And at x equals L, this becomes c sub 2L equals 0. So from this condition, c sub 2 equals 0. So c sub 1 and c sub 2 equals 0, y equals 0. When the lambda equals 0, solutions becomes y equals 0. Also, in the case of the lambda equal minus alpha squares, you could make a similar calculation. Y equals c sub 1 hyperbolic sine alpha x plus c sub 2 hyperbolic cosine alpha x. Then hyperbolic sine 0 is 0. So c sub 2 hyperbolic cosine 0 is 1. So this is 0. C sub 2 is 0. Substitute L. Then it becomes c sub 1 hyperbolic sine alpha L equals 0. So c sub 1 have to become 0. So you can substitute c sub 1 and c sub 2 is 0. So it becomes 0. So we have y equals 0. So in the two cases, lambda equals 0 or lambda is a negative quantities, y have to become 0. But when you consider the lambda is a positive quantity of the alpha squares, there is non-zero solutions. Lambda is a alpha squares. Then y is expressed c sub 1 sine alpha x plus c sub 2 cosine alpha x. Then you can substitute. So sine 0 is 0. So c sub 2 equals 0. Then for the second condition, yl is 0. So c sub 1 sine alpha l equals 0. So to satisfy this condition, if the alpha l is an integer multiple of the pi, then sine n pi is always 0. So we don't have to consider the c sub 1 is 0. So from this condition, you can find the alpha is expressed n pi over l. Once you find the alphas, lambda we could find, so n pi over l squares. This is the value of the lambdas. This is the eigenvalues of lambdas and the corresponding eigenfunction of the y. So we have already studied the trigonometric function of the sine form the orthogonal set of functions. You might wonder if it is possible to find a set of orthogonal functions from solution of boundary value problems. So I'd like to explain. We start with a regular Sturm Liouville problems. So we consider a very strange form of the differential equation. So d dx times r is a function of x, times y prime is a first derivative of y with respect to x, plus q is a function of x, plus lambda times p is a function of x, and lambda is a eigenvalues, times y equals 0. And the boundary values are given at the 2 points. At the x equal a sub 1, y plus b sub 1, y prime equals 0. And also at the x equal b, a sub 2, y plus b sub 2, y prime equals 0. So these are boundary conditions. If you consider a very simple case, in the last case, y2 prime plus lambda y equals 0. This is differential equations. y0 equals 0 and the yl equals 0. So if you compare this differential equation is a form of the regular Sturm Liouville problems, you can easily find r is a 1 and q is 0 and p is 1. And if you compare the boundary value problems, a is 0, a sub 1 is 1, b sub 1 is 0, b is L, and a sub 2 is 1, and b sub 2 is 0. This is a special case of the regular Sturm Liouville problems. Then I'd like to show you these solutions of regular Sturm Liouville problems form a set of orthogonal functions. So we consider the eigenfunction y sub m and y sub n, and the corresponding eigenvalue is a lambda sub m and lambda sub n. You can substitute y equal y sub m and lambda equal lambda sub n into the regular Sturm Liouville problems. You obtain this equation. And also you can substitute y sub n. You get this second equation. You can multiply minus y sub n for the first equation. You can multiply y sub m in the second equation. Then sum up these two equations. P lambda sub m y sub n y sub n. This becomes lambda sub m. Y sub m lambda sub n p sub n is here, this part. Then we can move this term to the right hand side. And also the product of the q times y sub n and the q times y sub n. This term is going to be cancelled out. Only the first term survives in the right hand side. This is exactly equal to this equation. Integrate a to the b's in the both sides of the equation. So lambda sub m minus lambda sub n. This is a constant values. And a to the b px y sub m y sub n dx. So this is equal to the a to the b minus y sub n d dx r y sub m prime dx plus a to the b y sub m d dx r y sub n prime dx. Then you can perform the integration by part. It becomes minus y sub n r y sub m prime a to the b plus y sub n prime r y sub m prime dx a to the b. So these two terms comes from the first terms plus y sub m r y sub n prime the b minus a to the b y sub m prime r y sub n prime dx. Then if you look at our second term and the fourth term is exactly the same, so we can cancel out. So finally it becomes, if you substitute the x equal b, so rb times y sub mb y sub n prime b minus y sub nb y sub m prime b minus r sub a y sub m a y sub n prime a minus y sub n a y sub m prime a. So this is the equations we derived. Then we consider the boundary conditions. first boundary condition is given by a sub 1 y plus b sub 1 y prime at x equal a equals 0. So we substitute y equal y sub m or y sub n. So we build the two equations for the y sub m and the y sub n. Then we combine these two equations in the matrix forms. So we have this matrix form of the equation. At least one of the value among the a sub 1 and b sub 1 is non-zero values. To satisfy this condition, determinant of the matrix have to become 0. So we derive this condition. Also, we use another boundary condition. So we could build the same matrix forms and another equation. So we have two equations. This is a condition for the boundary at the x equal b. This is a condition for the boundary at the x equal a. Both of them become 0. So finally, if you integrate p y sub m y sub n from the x equal a to the x equal b, it becomes 0. So from this equation, we could discover the weight function is given by the px. This p corresponds to the weight function. Then I'd like to explain the singular Sturm Liouville problems. The same differential equation we considered, but the boundary condition is different. Sometimes Ra equals 0 and a sub 2 y plus b sub 2 y prime equals 0 at x equals b. Another case is a sub 1 y plus b sub 1 y prime equals 0 at x equals a, or r sub b equals 0. First case r sub a is 0. This is 0. And the second condition a sub 2 y b sub 2 y prime equals 0 at x equals b. This is 0. In this case, right hand side becomes 0. This is a case of the first case. The second case is r b equals 0. So second case is this is 0. And also this is 0. So right hand side becomes 0. The third case, r equals 0 at x equal a at x equal b. This is 0. The fourth case is a little bit complicated. This is periodic condition. Ra and equal rb. And ya equal yb. Y prime is equal at x equal a, x equal b. If you look at the right hand side of the equation, if these condition is satisfied, right hand side becomes 0. In the case of the singular Sturm Liouville problem, strange boundary conditions are given, but always the right hand side becomes 0, and we could explain the orthogonality of the functions. Then you might wonder how we can find the functions such as r. I would like to explain how to find them. Self-adjoint forms. So we start considering the very general form of the second order differential equations. A y2 prime plus b y prime plus c plus lambda dy. At first, we need to convert the equation into the standard forms by dividing by a. Then y2 prime plus b over a times y prime plus c over a plus d over a lambda times y equals 0. Then multiply the integrating factors of the exponential integral b over a dx. So you multiply the integrating factors in the equations. And then you can easily find out first two terms is combined into the single terms. You can easily find integrating factors actually correspond to the r. These terms correspond to the q, and these terms correspond to the p. Okay, so I explained how to find the functions of r, q, and p from the general form of the differential equations. Okay, this is the end of this session.